Welcome back, class. Last time we left off on the water cycle, which is one of the factors that affects our climate. Next factor that affects our climate is the atmosphere. You have to think of the atmosphere and the ocean, actually, as kind of like an air conditioner. Okay, it does cool, it does heat up, depending on what's going on. Now, when we're talking about the atmosphere, of course, this is gases, right? They're swirling around. There is a pattern, somewhat, how these gases swirl or blow around our planet, and it depends on what's going on, though. Okay, so air temperature and pressure are going to change with altitude, and this is going to push and this is going to pull different types of weather to different areas of the globe. So these things that are pushing and pulling are air masses. So these air masses, they're going to be different. Okay, they're going to have a different temperature, their moisture level, whether it's warm, whether it's cold, whether it's hot, if it's really moist air, if it's really dry air, it of course is going to affect our weather. Moving on, fronts are where these two air masses meet up, and wherever these air masses, I said two, I didn't mean two, but there's air masses all over. Where these air masses meet up, we're going to see different types of weather patterns happening. Okay, and the more intense the difference, the more intense the weather. So if you have a really, really cold front and a really, really warm front, where they meet up, you can expect some extreme weather. Here are some fronts, how they meet up, and what you can expect. Now I'm going to want these pictures to be put on page 9 of your notebook. Make sure they're hand-drawn, color being important. If it's cold, make it blue. If it's warm, make it like yellow, red, something that signifies that it's a warm type of air mass, okay? Now, if we look at this map here, we can see how cold fronts and how warm fronts are shown on a weather map. If we look at this over here, we can see how most of our cold fronts are coming from, excuse me, all of our cold fronts are coming from the north. That makes sense. We're going towards the poles. Cold fronts are going to be coming down from the north and down to the south. Our warm fronts, however, they're going to be coming from here, okay? The Gulf of Mexico, and then also here. In the summertime, it's kind of interesting to see what goes on for a lot of our thunderstorms during the summer, which we didn't have very much this year. They happen down here, and they swirl up. They're usually old hurricanes that hit land, broke up, and we get some of the remnants of that hurricane. Now, when we're talking about air pressure, and you don't really think about air pressure too much because really, air is light. But a good way to kind of show off that we do have air pressure is when you go up and down in any type of elevation. So if you were to go up to Big Bear or up to Arrowhead, you'll notice that the pressure changes because your inner ear, you can feel that pressure change in your ear. And it's always a good idea to chew some gum. That way your ears slowly release that pressure instead of all at once it pop, because that can actually hurt. Another example of this, which is more extreme, is when you jump in a pool and if you dive down, you can feel that pressure, okay? It's more extreme, of course, because water weighs more, but atmosphere or air does weigh, so it's that pressure bearing down on us at any given time. The pressure is going to be higher naturally at sea level, and it's going to be lower the higher you go up in elevation. Now, beyond this, there's also air pressure caused by cold air dropping or warm air rising. So if it's warmer in any given area, you typically end up having a lower pressure where it's warm because that warm air is rising up. If we have cold air coming down on us, we're going to have a higher pressure. So we do measure air pressure with a barometer, and very similar to what I was saying earlier, it measures how much pressure is bearing down on us or the lack of air pressure on us. So if we look at a barometer and we see the air pressure is falling, meaning we have lower pressure around us, we can expect stormy weather to come. We're pulling it towards us because it's lower pressure. Versus rising air pressure, if it's bearing down on us, we're pushing it or blowing it away. Okay, if it's steady, whatever you got, you're stuck with that weather. Winds also make a difference. These also can create high and low air pressure. We kind of talked about this when we were referring to the Santa Ana winds. So if we look at behind our mountain range, when Santa Anas are going, there's going to be a lot of pressure there. We're going to have lower pressure in comparison to the back of our mountains, and the greater the difference is. So if we have a really low area, really low pressure here in San Bernardino, and a really high pressure in Hesperia and Victorville, we're going to have a more increased wind factor. Now, we don't necessarily see a really low air pressure in our area, but what we really see is a really high pressure on the backside of our mountains, created by that cold snap in Colorado and all that air pressure coming back and hitting the back of our mountains. We also have global winds. So I'm going to take a break here for just a sec and show you guys a little video. It really clears some things up.
I'll hold the sun.
Because of the shape of our planet and the way it tilts on its axis, the sun heats Earth unevenly.
Direct rays hit the equator,
But towards the polar regions, the rays hit at an angle.
so the energy spreads over a bigger area?
Direct concentrated rays make it much hotter here at the equator.
And cooler at the poles.
Right. Warm air at the equator rises, creating an area of low pressure. As it rises, this warm cools, and then
Cool air sinks. So farther north, that cool air must come back down.
yes, and where it comes down, it makes an area of high pressure. These are desert regions. This constant movement of air between low and high pressure regions causes global convection cells.
60 seconds of silence.
We can demonstrate a convection current by using this convection apparatus. I've lit the candle under this chimney. The heated air from the candle rises, same as warm air rises from the surface of the earth. Cold air rushes in to take its place. This cold air is heated, and it rises, allowing more cold air to take its place. Eventually, we set up a circular current. And, if we had smoke, you can actually see the current. Smoke is being carried along in a convection current. If you think of the candle as the sun at the equator, warm air rises, then cools and sinks back down to Earth in the desert regions, while at the equator, more air is warmed and rises.
Back to Earth. Convection currents are pretty straightforward, but because we're dealing with planet Earth, we have to add a spin to it.
Earth's rotation. That must change the convection currents.
It does. We can use this globe to show how the rotation bends or deflects the currents. Try drawing a straight line from the North Pole to the equator.
They all curve the same way.
This is known as the Coriolis effect. It drives the three dominant winds on our planet. The trade winds, the westerlies, and the polar easterlies.
And here at the equator, there aren't any winds?
No. Along the equator, there are no prevailing winds. This is where we find the doldrums. Do you know which winds drive our weather?
Most of our weather systems come from the west, so they must be driven by the winds from the west.
Right, the westerlies. Now, what we've looked at so far is only part of the global weather picture. There are other winds. Jet streams in the upper atmosphere zigzag around the globe at extremely high speeds. They transfer heat from the tropics to the poles.
And cold air from the poles to the tropics?
Exactly. That's a huge system for transferring hot and cold air around the globe.
One of the main reasons we have these global winds is because we have hot air at the equator. This hot air, it's going to rise at the equator. It's going to go up in the upper atmosphere, and as you get higher up, things cool off. So that air is going to cool off, and it's going to drop down. It's going to drop down in areas of what we typically refer to as our temperate areas. Okay, so this cold, dry air, because remember, as things cool off, it also condenses and squeezes that water out. So it's going to come up from the equator, warm and wet. It's going to rise up. It's going to drop that water. It's going to cool off, and then it's going to come down. And we have the cyclical effect at the equator into these temperate areas, both in the northern hemisphere and also in the southern hemisphere. Continuing on with our atmosphere is this idea of relative humidity. And what relative humidity does, it measures the amount of moisture in the air compared to what the air can hold, because air itself can hold more or less humidity dependent upon what. Now that what it is how warm or cold that air is. So the warmer the air, the more moisture that air can hold. So it's relative to the temperature. Okay, that's what we mean by relative humidity. So the warmer it is, the more water can fit itself, the more water molecules can fit itself in this less dense air. The colder the air, the more dense the air is. Those of you who are into cars, the colder it is outside, the more oxygen can get into that combustion chamber. So they have certain ways of cooling off that air in order for it to get into the engine prior to combustion. And having that more condensed air causes a more violent combustion. So you're going to end up having more horsepower because of that. So 100% relative humidity is completely saturated air. So if you pay attention to the news and they say the relative humidity is in the 70% and up, you're going to have a whole lot of humidity. Now, typically, every evening, not recently, I don't think, we do hit 100% relative humidity when the air is completely saturated and it can't hold any more water. And this is when we get dew, okay? When it cools off at night, that air condenses and it squeezes out. As it cools, because it's nighttime, there's no sun, it squeezes, it becomes more condensed, that air itself, and it releases water, and we refer to that water as dew. So typically every night we do get some dew. Not always though, when it's really, really hot and it stays warm outside at night. So as I was saying before, controlled by temperature, warm air holds more moisture than cool air. There's just simply more space for that water to fit itself into. As air warms, relative humidity decreases. You guys get that, right? So that can be a little counterintuitive. That number actually decreases because you're making more room. So as that air warms up, you're creating more room. So that number, relative humidity, decreases because now there's more room. As air cools, relative humidity increases because there's less room and not as much water can fit between those air molecules. A few questions for you guys to think about that were answered previously. Let's go ahead and move on to our ocean. That is one of the other factors that affects our weather. And like I was saying before, we have to think of both our atmosphere and then also our oceans, and particularly our oceans, as an air conditioner. Because what it's going to do is it's going to bring coolness or it's going to bring warmth to us. It kind of depends on what the ocean is doing. So in our area, we do typically have a cooler ocean current coming towards us, and it gives us a cooling effect. However, sometimes that ocean current is warmer. It varies from year to year. They'll talk about on the news sometimes how people are catching fish off of our coast that are typically tropical. If that's the case, we know we're in for some warmer weather, typically a warmer winter. Temperature changes affect our pressure, which also creates winds. If you guys notice, if you're ever at the beach, There's typically some type of breeze going on, and it's because of these temperature differences.